In this video, I'll do a couple more examples of using measured data to estimate linear relationships for systems. The first example will be a strain gauge. The second is a height measurement system. This is a strain gauge. It consists of a thin wire or thin piece of metal foil which connects to these two terminals. When the strain gauge is stretched or bent, the wire or foil will stretch. Stretching or compressing the wire makes it either longer and thinner or shorter and thicker. This causes the electrical resistance of the wire to change, since long, thin wires have higher resistance than short, thick ones. Strain gauges are bonded to a piece of equipment to measure the amount of deflection the equipment is experiencing. I'll use a strain gauge to measure the deflection of this plastic beam. I've simply glued the strain gauge to the beam here. For this system, our input will be the deflection of the tip of the beam, and the output will be the resistance change of the gauge. Before we take the data to characterize the system, though, let's talk a little more about the system itself and why strain gauges are useful. In block diagram form, our system looks like this. The system itself is a combination of the beam and the gauge. The input is the vertical deflection of the tip of the beam, which I'll call Y-tip, and the output is the resistance of the gauge, R. The units of input are centimeters, and the units of resistance are ohms. The strain gauge provides a resistance change for a given deflection. From the measured deflection, we can create mathematical models predicting the stress of different objects. Once we know what stress the part will experience, we can decide whether we expect the part to break, or we can redesign the part so that it won't break under the expected operating conditions. Now let's take some data on our system and estimate a straight line that approximates the system response. I'll measure the resistance of the strain gauge with this digital multimeter. When the beam is undeflected, so that Y-tip is 0, the gauge resistance is about 120 ohms. I'm going to set up my sign convention so that positive deflection is down. If I push the beam tip down as far as it'll go, the maximum deflection is about positive 6 centimeters, and the resistance becomes 120.6 or 7 ohms. That gives me 2 points that I can use to estimate a straight line, but for future reference, I'll get a third data point by raising the tip of the beam. Since positive is down, the deflection at this point will be about negative 6 centimeters. At this deflection, the resistance of the gauge is about 119.2 ohms. Now let's use the first 2 data points to estimate the equation of a straight line and then see how well that line predicts the resistance at the third data point. This is the assumed form of the linear relationship that governs our system. The resistance of the strain gauge is some slope times the tip displacement of the beam plus a y-intercept. These are the 2 data points we're going to use to estimate M and B. M is the slope of the line. It's just the difference in R divided by the difference in Y. So this is 120.7 ohms minus 120 ohms divided by 6 centimeters minus 0 centimeters. This is 0.7 divided by 6, which is about 0.117 ohms per centimeter. That gives us our slope. Once we have the slope in here, we can use either of these points to estimate the y-intercept. I'll use this one. So the resistance, R, is 120 ohms, is equal to M, which is 0.117 ohms per centimeter, times the tip displacement here, which is 0 centimeters, plus B. This cancels as 0, so B is equal to 120 ohms. Now we have the numbers necessary to fill in the blanks in this equation. Now let's see how the equation we've estimated from these 2 points agrees with the third data point that we took earlier. This is the linear relationship between the resistance of the strain gauge and the tip displacement of the beam that we previously determined. We also took a third data point where we deflected the tip of the beam up by about 6 centimeters. Since positive is downward, that corresponds to a negative 6 centimeter displacement, and we measured a resistance of 119.2 ohms. Let's plug this displacement into here and see how close our estimate agrees with our measured data. So from our estimate, R is equal to 0.117 ohms per centimeter times the tip displacement, which is -6 centimeters, plus 120 ohms. This turns out to be about 119.3 ohms, which is pretty close to our measured value. So this system looks like it's actually fairly linear. The final example is an acoustic proximity sensor. This type of sensor uses the echo of an ultrasonic wave from an object to estimate the distance between the sensor and the object. In our system, we'll measure the height of an object above the sensor. So the input to our system will be a height, and the sensor will output a voltage that indicates that height. We need to estimate the mathematical relationship between height and output voltage of the sensor, and we'll assume that that relationship is a straight line. This is the sensor we'll use. The ultrasonic signal is emitted and its echo is measured here. The round trip time of the wave is measured, and internal circuitry in the sensor converts that time to a distance. A voltage output is provided at these terminals, which corresponds to the measured distance. This is the system we want to characterize. I want to measure the height of this styrofoam plug. I'll use this DMM to measure the voltage output from the sensor and this power supply to provide power to the sensor. When the plug's at the bottom of the tower, the bottom of the plug is 7 inches from the sensor and the measured voltage is 0.074 volts. If I raise the plug to the top of the tower, the bottom of the plug is now 30 inches from the sensor and the output voltage is 0.28 volts. Now let's estimate the equation of a straight line that relates the output voltage to the height. This is the assumed form of the relationship between the sensor output voltage and the height of the styrofoam slug. We want to use these two data points to determine M and B in this relationship. M is the slope, it's just the change in voltage, 0.28 volts minus 0.074 volts, divided by the change in height, which is 30 inches minus 7 inches. This turns out to be about 0.009 volts per inch. Now, having this and any one of these data points, I'll use this one, we can estimate B. B is equal to the voltage, 0.28 volts minus M, which is 0.009 volts per inch, times the height, 30 inches. This turns out to be about 0.0113 volts. So these are the numbers that go in this relationship to model the difference between voltage and height.